Hello everyone, welcome to the first lecture of week 5 on the course Power Network Analysis. In this particular discussion, we will continue with our fourth main module, which is evaluation of transmission line parameters. And in the previous week, we were continuing our discussion on the same topic where we have reached at the fact that if we have single strands or single conductors, transmission line conductors, how do we evaluate the inductance? How do we figure out their flux linkages if there are a group of conductors? And based on that, today in this discussion, we will take up our topic of inductance evaluation for actual three-phase transmission lines. And as I have mentioned, we'll take up our discussion based on the last week's last lecture discussion where we had concluded with how to evaluate inductance of composite conductors. That was still not complete, but this inductance evaluation is significantly dependent upon the magnetic flux linkages which a conductor might experience due to several group of conductors carrying respective currents. And what we had seen that if we have two composite conductors, composite conductor A and composite conductor B, one of these conductors is acting as a return path for the other conductor. So it is analogous to the case of single phase two wire circuit where we had chosen only one conductor per phase or per wire. We are complicating or sort of expanding that single wire to be a ACSR conductor of some form. There are different types of ACSR conductors with different strands of steel wires or steel strands in between and different number of strands of aluminum wires coupled or wound around those steel strands. So the number of strands in these ACSR composite conductors could be different. And in composite conductor A, we had chosen N as the number of strands. Composite conductor B has M number of strands. And we have assumed that these conductors or strands are parallel. Their current distribution is uniform. The respective strands have the same current density. So given the fact that if at one point of time composite conductor A is carrying current I, which could be a AC current or a DC current, and since composite conductor B acts as a return wire or return path for conductor A, so at the same time instant conductor B would carry current minus I, and since each of these strands are assumed to have the same quantum of current, so basically each strand in conductor A is carrying current I by N, and each strand in conductor B is carrying current minus I by M. By N and by M refers to the number of strands present in individual conductors. And using the notion of evaluation of magnetic flux linkage of a specific conductor with respect to currents present in other conductors. So these other conductors, they could all refer to remaining n-1 strands in conductor A or the M strands carrying current minus I by M respectively in conductor B. Because of these different currents as well as the current which conductor A is also carrying, what was the effective flux linkage of conductor A with respect to a point at infinity, and from there we had figured out the inductance value of strand A in composite conductor capital A, and on similar lines we can also evaluate the conductance of strand B and so on till the nth strand. For composite conductors A, similarly, we can also find inductance of A dash strand, B dash strand goes on till M dash strand or M basically in composite conductor B. And since these strands, they are all parallel to each other, if we specifically focus on one set of conductor or one composite conductor, then using those individual inductances, we can take the average value which is indicated by this expression here, LAV comma A, AV small representing the term or notion average. If we take up the sum of individual inductances divided by the number of strands that we have, then essentially we have this sort of expression. And this is where we had stopped in our previous week's previous last lecture's discussion. Before we proceed further, let me point out or focus on certain aspects that would be very useful for today's discussion. If we focus on the numerator, which is the term sitting over here in LAV, comma A, how many number of distances, or basically what type of distances are these capital D's representing? So if I, let's say, talk about DAA dash, DAA dash is nothing but the center to center distance, which is, let's say, center over here. Then similarly, strand A dash has a center over here. The distance between these center to center strands is AA dash, and similarly DAB dash is, let's say, if this is my strand B dash, then from center of strand A to center of strand B dash, the corresponding shortest distance is DAB dash, and this goes on till we reach the center to center distance between strand A and strand M. That is where DAA terms comes in. So the numerator essentially is consisting of distances between one, if I focus on, let's say, one group, let's say this group, which is with respect to center of strand A, then these distances are M in number, and these distances are distance of center of strand A with respect to remaining strands in composite conductor B. Similarly, if I focus on the next group, then this is basically product of distances of strand B in conductor A with respect to center of strands of center of the strands present in composite conductor B, and this goes on till I am evaluating the distance to distance, center to center distance between strand N with respect to other strands in composite conductor B, strand N being in composite conductor A. So essentially all these groups, if I focus on, then one group is consisting of product of M distances. Similarly, the other group is also product of M distances, and this goes on till I reach the last group, which is also product of M distances. And basically how many number of groups of these products I would have? I would have the same number of groups as many number of strands are present in conductor A, which is N. So essentially the numerator without the 1 by mth root, it is essentially the product of N comma M distances for which 1 by mth root is being taken, and that is all about numerator. If we talk about the denominator sitting inside the natural log term, the denominator is nothing but center to center distance of strands within one conductor, which is conductor A. So AA is nothing but the self radius. For inductance, it is R dash, or basically R into e to the power minus mu r by 4. Where, so let me write that. So DAA, DBB, assuming these strands are of the same type with the same radius, this is nothing but R into e to the power minus mu r by 4, by where mu r is relative permeability of each individual strand. Usually electrical conductors are poor magnetic material, so mu r is close to 1. So this is the individual self distance or self radius of each strand, and if I focus on one particular group, this strand or distance is basically products of n distances, and this goes on till the last group. So if I focus on the denominator, essentially I have n comma m distances whose products are being taken, and then the corresponding 1 by nth root is appearing in. So with that, if this explanation is acceptable, if this is okay for those, if this discussion is complicated or could not figure out how these expression came in, I request the viewers to please go back and look the previous lecture which we had discussed. So from there things would definitely become clear. So with this, we have figured out an average value of the inductance of all strands in conductor A. Since these strands are all conductors which are assumed to be in parallel because magnetic field distortion is not happening, magnetic flux lines are all concentric, the wires are all straight, there are no bends, etc., etc. So essentially, since these strands are all in parallel, they are of the same nature, their current in essentially for individual conductors, the currents are also the same. So essentially LAV comma A, which is average of the inductance of all strands in composite conductor A, these strands could be assumed to have this inductance where have the same inductance because their properties are more or less same. So LAV comma A would essentially indicate this approximate inductance value which would be common to all strands in composite conductor A. Similar expression could also be written for a particular strand in composite conductor B, and then its average could be taken. And since these strands are of similar material, similar type, their if the inductances were to be same, then LAV comma B would indicate the corresponding inductance of every strand in composite conductor B. So assuming that these strands are all parallel, their current distributions are same, and if we have to find or sort of make our evaluation a little simpler, then assuming that this is true, that LAV comma A is the inductance value of each strand in composite conductor A. So essentially we would be left with a situation where from sending end, let's say, to a receiving end, if I have a transmission line moving on from node A to node B, and I'm focusing on one conductor, this conductor has n parallel strands running through it, which is, let's say, n number of strands, and each of these strands is having an inductance of L average comma A. If I have to find the overall inductance of all these lines combined together, then if you recollect, if there are resistances in parallel and if I have to find their equivalent resistance, similar logic could also be applied to find average or equivalent inductance if the circuit is consisting of n parallel inductors. So essentially the overall inductance or L effective inductance of composite conductor A would be nothing but LAV comma A by N, which is coming in from the fact that there are n parallel inductances of the same value. So essentially, let's say if I have to find the equivalent inductance, how do I get this expression? Let me explain that. You have to find the effective inductance of n parallel inductances. What I would have done, I would have taken the inverse of individual inductances, and then I would have added these inverses till the strand. So since these inductance average is the same for all strands, so basically if I add this up and simplify, I would get this number. So since there are n parallel strands, each having the inductance L average comma A, then the effective inductance as discussed in the previous slide would be 1 by n times of L average comma A. So basically effective inductance is 1 by n of L average comma A. So this 1 by n factor, this again gets reflected over here in the natural log numerator and denominator. And now if I see, if you recollect our previous slide discussion, the numerator is product of n comma n inductor distances and the denominator is product of n comma n distances, and for the numerator 1 by m comma n or m into n root is being taken, and for the denominator 1 by n into n root is being taken. So effectively, if I have n square distances sitting in the denominator, I am taking the 1 by n square root of n square distances. So essentially this becomes one individual or effective denominator distance. And similarly here I have m comma n distances for which 1 by m comma n root is being taken. So this also turns out to be a effective distance where the number of distances and the corresponding root effectively the effect gets cancelled out. Or other way around, if I were to say, it appears that, not does it appear, but effectively this distance or this product sitting in the numerator of natural log is nothing but the geometric mean of m comma n distances, similar to defining arithmetic mean, and similarly this term here is geometric mean of n comma n distances. Geometric mean, it's all about multiplying and then taking the corresponding root. Arithmetic mean is adding these terms and then dividing by the number of terms that exist. Similarly, I can also find the effective inductance of a composite conductor B, which is the overall inductance of conductor B, because it has m strands are in parallel, and similarly the way L effective A is evaluated, and on similar lines L effective B can be evaluated. What we see here in these terms is something interesting. The interesting part is, if I compare the numerator of the natural log term of L effective B with the numerator of the natural log term of L effective A, they are exactly similar terms. The product pairing wise, the notions are different, but if I, let's say, focus on DAA dash, DAA dash is present here, it is also present over here. DBA dash, this is present in this group, but in the other group, DBA dash is the first term. So similarly, DNA dash, it is appearing as the first term in L effective A. So essentially, these two numerator terms, they are exactly the same. The denominator terms are, however, different. The denominator, however, in L effective A is geometric mean of n square distances, which are center to center distance between the strands, and for L effective B, the denominator is geometric mean of m square distances, where these distances are center to center distance between strands in composite conductor B. So with this, we now have our expressions, or I would say simplified version of inductance evaluations for conductors A and B. What appears to be boggling is that if the number of strands are more, or if the arrangement is complex, then one probably has to evaluate these distances in order to find these inductances. And if you recollect, in the previous lecture, I had given little clue that there are ways of how these distances need not be evaluated, and still the evaluation of inductances can still be done. So let's see how it is done. So in the previous expressions of inductances, the numerators in the natural log terms, as I mentioned, they are the geometric mean of the distances. So we call them as geometric mean distance, in short GMD, which is m comma m into nth root of m comma n distances. And similarly, for so it's effectively this GMD is indicating that if I were to represent composite conductor A consisting of n strands and composite conductor B consisting of m strands as two effective single conductors. So basically, instead of having n strands in conductor A, there is only one conductor in A, and similarly, if there is only one conductor in B, then the center to center distance between these two analogous conductors is nothing but the GMD itself, which is essentially what is written here. GMD is the effective distance between space centers of composite conductors A and B. If we could figure out analogous conductors which can replace composite conductor A and B respectively, then GMD is the center to center distance. Similarly, the denominator in the natural log term, it is also the self GMD of the conductor, and it is to sort of differentiate it with from GMD, it's given a term geometric mean radius GMR, which is the n square root of the n square n distances in conductor A and m square root of m square distances in conductor B. These distances, if you compare, they are the self radiuses or the center to center distance between strands in a particular conductor. So given that we now understand what is GMD and what is GMR, let's see how these can be furthermore simplified. So effectively, in terms of GMD and GMR, effective inductance of A, effective inductance of B can be written, and since this represents a single phase two wire circuit where the space between these two conductors have additive magnetic flux lines, the way the currents are flowing in them as per right hand rule. So effective circuit inductance, the way we did it for single phase 2-wire circuit, the effective inductance is addition of inductances of respective conductors A and B, similar to single phase 2-wire circuit discussion. The beauty here is that since these conductors are manufactured by some manufacturer, so manufacturer very well knows what type of ACSR conductor this conductor is going to be, what type of ACSR conductor this conductor is going to be, and they understand or they know what number of steel strands are present in the center, how many aluminum conductors are present over the steel strands, what are the individual radiuses of these strands, what are the center spacing between these strands. So as manufacturers, they automatically, when they supply these transmission lines, because essentially talking about evaluation of inductances for transmission lines. So the manufacturers, they provide a data sheet or a table in which the GMR of the conductor is essentially defined or calculated by the manufacturer. So usually GMR need not be evaluated if it is a line provided by a manufacturer. If for the sake of numerical discussion one needs to still verify whether, okay, let me figure out the GMR, using the data sheet provided by the manufacturer, one can again use these expressions to verify the GMR. In the last discussion of this particular module, we will also understand how numerically we can verify these GMR values from the specification given by the manufacturer. And for GMD, if the strands or conductors are spaced apart in the sense that the center to center distance between the conductors is very high, then effectively the GMD which I was talking about over here in this particular context, as the distance between these conductors increases, even if we evaluate the GMD as per the actual expression given over here, there might be little inaccuracies in terms of number of decimals present in the distance that we were going to evaluate. But suppose one doesn't want to evaluate GMD the way it is given over here, because it's a very complex expression. One has to keep account of the mapping between the strands, the distances which are to be evaluated. If the distance between conductors is pretty far off, then GMD will essentially be nothing but the space distance, center to center space distance between the geometric centers of these conductors. So essentially in terms of GMD, if the distance between conductors is pretty far off, GMD is approximately equal to center to center distance between these two conductors. The center to center distance are the effective centers or equivalent centers. So in a nutshell, GMR and GMD, they are rarely evaluated in practice. They are mostly commonly available. The GMR part is from the manufacturer, whereas for GMD one can approximate the GMD evaluation by considering fictitious center to center distance between the conductors themselves. One who still wants to very precisely, accurately evaluate inductance, you are most welcome to make use of those inductance expressions with GMD being the sum root of some distances. So coming to our main focus of discussion, which is inductance evaluation for three-phase lines. The concepts that we have learned for inductance calculation in single-phase circuits, they can still be applied to three-phase lines. And for three-phase lines, I mean that at least there is one composite conductor assigned or dedicated to one phase of line. And I'm assuming that these lines are operating in a balanced condition, meaning that these currents are positive sequence currents IA, IB and IC, and IA, IB, IC are symmetric vectors. So basically their magnitudes are same and their phase angles are 180 degree apart. For symmetrical spacing of three-phase lines, I mean if I have one composite conductor for phase R, one for phase Y and one for phase B, then for symmetric spacing it means that these conductors are placed at the same distance from each other, which is, let's say, distance D, and if the distances have to be the same, then essentially it appears that these conductors are placed at the tips of an equilateral triangle whose side is D. Each of the sides are D. That is what is meant by symmetric spacing. So if I have a symmetrically spaced three-phase balanced line and I have to find the inductance of each phase or each line, then the way we evaluated inductances for composite conductors in the previous discussion, I would just have to know what is this GMR, which is usually provided by the manufacturer. And since the spacing is symmetric, so even if I evaluate the actual GMD, it would more or less be same as the physical symmetrical spacing, which is D. So once this D is known because of the arrangement of three-phase lines, depending on how the towers are constructed or how the towers are positioned, the expression of L can be used here. So far so good, but there is every story has a twist. So for inductance of three-phase lines, there again exists a twist. The twist here is that these three lines in a three-phase system need not always be symmetrically spaced, because our tower constructions are different, our tower designs are different. You would rarely find a tower, or you would have seen very few towers where this symmetric arrangement is ensured. So for the sake of tower design, again from the tower safety perspective, if the symmetric spacing is not ensured, what would happen? The inductance of phase R, inductance of phase Y, and inductance of phase B, they would become unequal. And even if the load is balanced, generation is balanced, the transmission network which would carry this current from generation to load, the network itself would be unbalanced because of these unequal inductances. So there would always come up a possibility where no matter how much balanced operation one wants to have, because of network structure, the overall operation can become unbalanced. And that is the twist which is there. So what is done to avoid this unbalance entirely? So essentially flux linkage will be different irrespective of whether the source or the load is balanced or unbalanced. To avoid this unequal inductance, to avoid this unbalance in the circuit, these conductors are placed or exchanged, their positions are exchanged at few regular intervals. We call those special towers where this exchange happens, we call those towers to be transposition towers. These are specially designed towers placed at few kilometers or miles distances. The frequency of occurrence of transposition towers is not common. These conductors, three-phase conductors, they exchange their position with respect to other conductors over a length of equal distance. So let's say if there is a line of 800 kilometers, so essentially the conductors would change their position at every 160, 170 odd kilometers, so that in an entire 800 kilometer span, every conductor of a particular phase occupies the place which other conductors would have taken up. So effectively, if we were to focus on one section, then yes, the inductance values may be different. If we focus on the next transposed section, the individual inductances may be different, so imbalance may exist. But at the entire stretch, if the symmetry is maintained, then overall the entire stretch, the effective inductances, they would more or less turn out to be balanced. The values would turn out to be balanced. So for this arrangement, we call that to be a transposition arrangement where the conductors exchange their positions at specially designed towers known as transposition towers. So what I have here is an arrangement of a transposed three-phase line. I am associating the phases to be small a, small b, small c. They are not the strands now. So assumption here is the same, that the conductors or phases or lines in three-phase line, they are similar to each other. Their material is same. So basically the GMR is same and the currents are balanced. So essentially at any point of time, IA plus IB plus IC is equal to 0, because in balance condition we have seen how these sums turn out to be 0. So at one section of this transposition, which is section number 1, the other section is section number 2, transpose section, and then I have section number 3. If I have to find the inductance of conductor A in section number 1, which is what I am associating over here, A is phase A conductor, 1 here refers to the transposition section in which the inductance is being evaluated. This is the phase number or the conductor number. And if we recollect our flux linkage expression which we discussed last lecture, then at section A, conductor A is placed over here. Its distance from other conductors B and C are at distances D12 and D13 respectively. The GMR is known by the manufacturer or provided by the manufacturer. So if I have to find the flux linkage of phase A at section number 1, I have this sort of a expression, which is lambda A1. Please recollect or revisit the last to last discussion where we figured out how this flux linkage, magnetic flux linkage expression can be obtained. If this is the expression of phase A linkage at section 1, then can you guess what would be linkage of phase A with section 2 or in section 2? So in section 2, if you see, phase A has now taken the position of phase B, and phase B has taken the position of phase C, and C has now taken the position of phase A. So in these distances, a rotation or basically a shifting of positioning has happened. And in this shifting, it is essentially done in a anti-clockwise fashion. So A is sitting over here. And now the distance between phase A, phase B and phase A, phase C conductors are D23 and D12, unlike D12 and D13 respectively. So lambda A2 would be minus mu naught by 2 pi into IA, natural log of GMR, which is the self radius, plus IB. And now IB and IA, they are spaced apart at distance D23. So natural log of D23 plus IC, the C conductor and phase A conductor at distance D12. So natural log of D12 Weber turn per meter. Similarly, lambda A3 can be evaluated on similar lines. So if you evaluate that, then these are the expressions that we would get at different transpose sections. And the way, since the same conductor is taking up different values of inductances or flux linkages at different sections, so one way, common way is to take the arithmetic mean of these flux linkages. So if the average flux linkage of conductor A is to be obtained after all transposition is done, then essentially we have this expression here, which gets simplified to this. And remember, our system is balanced. So essentially IB plus IC is equal to minus of IA, which if remodified and rewritten gives us this beautiful expression. So essentially we end up again with a analogous GMD between the different D-phase lines placed at different sections with effective GMR remaining the same. So overall inductance is this. Similar expression could also be written for other phase conductors. So DEQ is effectively the equivalent GMD, which is the geometric mean of spacing between transposed conductors in three-phase lines. Usually, three-phase lines, there are more than one conductors, which is essentially the reason behind bundling. Composite conductors are that one conductor is made up of several strands. Bundling is that one phase consists of several such composite conductors. And why bundling is necessary or needed? Bundling effectively helps in reduction of corona loss. It helps in reduction of effective line inductance because effective GMR goes up. As a result, the line performance is improved, which we will see in the next module. The radio interference and surge impedance also goes down. So we'll see also about surge impedance in the next module. Please have patience till we arrive at how these numbers or what these numbers are or what these values are and how the performance gets improved. So typically bundled conductors, they would have two or more than two composite conductors arranged symmetrically for every phase. So how do we evaluate these inductance in such cases? Also, these composite conductors in a particular bundled arrangement, they are physically spaced apart, which is usually symmetric arrangement, and they are separated at frequent intervals by some mechanical devices known as space dampers, which provide or prevent clashing, prevent contact between these conductors. So basically, if I were to typically draw the diagram of a space damper, if you had have seen a four bundle transmission tower, one bundle consisting of four conductors in an overhead transmission line, then if this is my space damper, which is usually a insulated device, the conductors or bundled composite conductors, they are placed at the tips of this space damper, and this space damper is essentially connecting or attaching these four conductors, composite conductors, while also avoiding physical contact with them, and it aids, provides mechanical damping in case of bad weather. It avoids the overall transmission line to sway away at larger radiuses. So it does have its own benefit. So for inductance of bundle conductors, what we have understood so far is, in order to find inductance, we essentially have to understand what is the GMD and what is the GMR. Now for individual conductors, the manufacturers are providing the GMRs. So for bundled arrangement, if I have a phase which is consisting of two composite conductors or two bundles, or in one bundle there are two composite conductors, and each conductor has self radius of r dash, where r dash again is r into e to the power minus mu r by 4, then the GMR is nothing but the fourth root of all four distances that can come in. Remember, GMR is the geometric mean of all possible center to center distances within one composite arrangement. So if I have r dash as the self radius and d is the distance between them, then d11 is r dash, d12 is d. So basically this is one group of distance. And similarly for other conductor, the self radius is r dash, which is the first term, and d21, which is the distance from here to here, is r dash d. So effectively fourth root results in r dash d square root. For three bundles which are symmetrically spaced apart, I'll have 9 distances, each distance or each couple or pair having 3 distances, and I'll take the corresponding 9th root. Similarly for 4 such bundle conductors, I'll have 16 distances, and the corresponding 16th root has to be taken. So with different bundle conductors which are symmetrically spaced apart, I can evaluate the GMR, obviously using the GMR of the manufacturer. So this essentially would be the GMR in the corresponding conductor which is provided by the manufacturer, which is for one composite conductor. So remember, each of these bundles or strands are composite conductors, and the distances that we are taking about are the center to center distance between the ACSR conductors. And depending on the GMD of how these bundles are spaced apart, DEQ is the equivalent GMD between center to center distance of respective bundles. With this, we conclude our discussion on inductance evaluation. In the next lecture, we will take up the discussion on evaluation of capacitance. Again, I request my viewers to please revisit these lectures or videos as frequently as possible to avoid having any doubts. Thank you.